Good day, guys. We now continue on the conceptual presentation regarding the amplification factor on the basis of how the AISC formulated the value of Cm. But before we move over directly to the suggestion of the AISC based on a research study, the concept of an equivalent moment ME uh, is here to be presented. The shown below is our moment diagrams upon which an equivalent moment may represent the value of Cm to be used for the moment amplification factor determination. So there are two possibilities upon which the magnification at this midspan of a brace column, that means the endpoints have no translation. So we may consider a triangular distribution of moment along the span and a trapezoidal distribution of moment along the span, upon which the main difference with this first end moment diagram and the second is that the slope of the primary moment diagram, so this is your primary, is much steeper than this moment diagram. So at the start of the effect of the secondary moment upon which your compression axial load acts with your delta due to the primary moment diagram, the secondary effect or the secondary moment may yield this curvature upon which this midspan value does not exceed the end moment at the ends. Okay, so we are referring to M2 again because M2 is greater than M1. But if the primary moment diagram is not as steep as this first condition here, the tendency for the midspan moment, which is based on this secondary moment curve, will exceed the bigger moment M2. Okay, and this too explains now the consideration of having a Cm value for brace columns or brace frames, because there's a danger that your M2, or sorry, your maximum moment will lie not at the ends, but rather at the middle of the beam span or the beam column span. So the equivalent uniform moment with maximum magnified moment of the midspan value shall now be used to capture the value of Cm upon which your moment magnification factor B1 will be computed. So taking the derived formula for MC max on the case wherein we consider unequal end moments, and also the value of FC max on the case where there is an equal end moment, we now equate these two, noting that in this equal end moment, we simply consider an idealization of this condition, noting that your moment here must be equated to ME for us to be able to solve for Cm, even though the condition is such that there are unequal moments applied at the ends. So solving ME in terms of M2 by equating the two equations here, okay, and considering that M here is equal to ME, we therefore extract the MZ max variable, and by mathematical simplification, we will yield this result. So this value here now is actually the Cm value that transforms your maximum moment at the end M2 into an equivalent moment ME. Okay, so Cm is rather a factor that simply converts your maximum moment, end moment, to an equivalent moment, okay, to represent this equation with equal end moments. So we also know that MZ max may be expressed in terms of amplification factor, such that your ME now here is amplified by using the first value of your amplification factor derived from the basis of the AISC. Okay, so this is our derivation on which was presented in the previous lecture, taking note that this value is simply the Cm value. And also for the MC max, the amplification factor now, if we consider M2, a variable will be inserted here. We take note that your MC max can actually be represented by Cm M2, and we simply divide it by 1 over 1 minus alpha to capture the moment magnification or amplification factor in general. Okay, so these two are again equated such that the relationship between ME and M2 simply falls on the variable Cm such that Cm is simply the ratio between the equivalent end moments, equal end moments, divided by the original moment, which is always the greater moment at the ends. So take note that in this particular formula for Cm, uh, we will note that lateral torsional buckling effect was not considered, and also the the effect of a double curvature case where M1 and M2 lies within this range is very critical. Okay, so it gives you a value which is not within the range of what we'd like to obtain from the value of Cm. So in short, AISC recommends a simple expression uh, that would represent this formula. ME here is actually a complicated formula here. No? So ME is based on this formula, here. Okay, so for us to simplify things out, the AISC recommends the use of this formula, and this formula happens to be shown in a form wherein there is a subtraction, no, of the second expression from the first. Originally, the AISC is actually recommending a positive, okay, sign here, since the value of the ratio M1 over M2 are always considered in terms of bending moment signs. Okay, when you say bending moment signs, you are considering the curvature, okay, rather than the rotation. So when you say curvature, we have two curvatures. So this is single curvature, this is reverse or double curvature. Okay, so this is actually positive, and this is negative. If you are going to use the negative sign here, you will take note that you simply base it on rotational moments, rotational sign convention. You might be confused. Other books have transformed this because they are using rotational sign convention maybe based on their analysis, especially when they do programs. Okay, so what happens here is that your single curvature is negative and your double curvature is positive. Okay, so this is only applied when there is no transverse load acting on it. But for types of beam column where transverse loads are acting, a fixed value of 0.85 for restrained ends and 1.0 for unrestrained ends, so you mean here the pinned ends, are recommended. So a very simple formula, but I would like to show you later how it compares with the derived formula above, to help us be convinced that the approximation of the AISC is very reliable. Okay, so with this problem, we take note of uh, case 2 scenario with transverse loading. No? So with transverse loading, we simply use CM is equal to 1 for pin end connections. So take note, we have derived this at the first video. So it is done using the differential equation method. So this is now my primary moment, okay, MO, the simply supported moment, and this is now your magnification factor B1. So B1 is simply this one. And of course, instead of having a KL over 2, where K is defined on the derivation as the coefficient of your differential equation variable y, equivalent to square root of P over EI. So we simply uh, uh, target, okay, the KL over 2 here. I think this part here is not KL over 2, no? So let's look at it by okay, it's a KL over 2. No. So I think this is a KL. So we'll check it later. I think this is only a KL squared. Okay, KL squared. But of course, we target KL over 2 here. We multiply this as L over 2. So I simply multiply it by the square root of L over 2. Okay, so a simple, I multiply it by L over 2. So this becomes originally square root of P, and then I insert L inside, so that becomes L squared. And then EI is there, so I insert a pi squared here because I have a pi at the top. So why do I need pi? Because I will be using a trigonometric function here, okay, to make this automatically in radians. So this is a pi over 2 square root of PL squared over pi squared EI. So what is this L squared pi squared EI here is actually your Euler buckling load. Okay, so it's 1 over PE. This is a PE, and 1 over PE. We know that in our derivation, this is always alpha. The variable alpha is there, but there's a squared sign, so this is square root of alpha. So we now substitute this directly on the secant formula there, and the KL over 2 also here. Okay, but here we need to multiply it by 2 such that this is now equivalent to pi square root of alpha here. Okay, so your KL is simply equal to pi square root of alpha. So you just remove the 2 there. So B1, based on the differential equation method, will now be this one here. Okay, by simply substituting value. And B1, using the approximate solution, is this one here, the one that we have derived also using the principle of area moment method. Okay, so this is now my psi. Okay, remember that this is your psi value, 1 plus psi alpha. So we now make use of what is delta O and MO. So delta O is a simply supported primary deflection. Okay, so this is based on a simply supported primary deflection formula. And MO is simply a simply supported maximum moment formula at the midspan. No? So that is MO. We substitute delta O and MO here, or simply a delta O over MO will yield this one here. So we simply insert it here. Okay. So what remains here is your pi squared EI over L squared. Okay. So simplification, you can cancel out that, you can cancel this. So what remains are actually real values. So 5 over 48 times pi squared minus 1 becomes 0.028, and this Cm becomes a 1 plus 0.028 alpha formula based on the case that we have presented. So for the value of B1, we simply put it Cm. This is equivalent to Cm over 1 minus alpha. Using the AISC formula, it's simpler. No? So this is Cm 1 minus alpha. There are no end moments. So 0 over 0 del will be equal to 1. Some uses a 0 over 0 as undefined. Some uses 0 over 0 or interprets as indeterminate. Okay? What's the difference between the two? So here I will explain to you why it can be considered 1 later. So this is 1. 0.6 plus single curvature, it's positive. Okay, so this is a positive 1 m1 over m2 1. So your Cm is equal to 1. Okay, so that's why if we are looking into the AISC recommendation, wherein the ends are not restrained against rotation with transverse loads acting, this is 1.0 automatically. So I just showed you how Cm was also derived based on this very simple but very accurate formula. So this AISC, very old but very dependable. And to compare them, using the MATCAD function, I simply defined a B1 based on the differential equation, approximation equation, and AISC equation. So I just make a function of alpha here, and iterate, or sorry, define a range of values alpha from 0 to 0.9. So what will I get here is this. And if you look closely, there's no difference, no? But there is actually a little error here. If you make use of a table comparison for this amplification factor, you will take note that when alpha is already around point 3, so you will notice that this starts to be deviating, and point 4 starts to be different until a certain time at point 8 they are no longer very near to each other, but still very reliable. So thank you very much for listening. So I hope you have gained a good understanding on how the amplification factor together with the Cm values works using 3 different techniques. I'll see you on the next video.